So what I would like to do now is to compare. People asked me whether or not these results are tighter than the ones we had before. So the way I'm going to convince you it's tighter is by showing you that under the same assumptions, I get a much better bound here than I got there. So let's start with a very simple case, which won't give me a much better bound, but I'm going to start with it anyway. And that's the case of the VC dimension. So assume VCF is D. Now, if you remember what we had, the result we had about the covering numbers, the L2 covering numbers, and this is the reason I all the time insisted on looking at LP covering numbers, not just L1, although in the previous bound I only needed L1. The fact is that the important covering numbers are in L2, not in L1. This is sort of an L2 type of result. So what I did, what Hausdorff showed is that the L2 covering numbers of a VC class are such that the log covering numbers behave something like an absolute constant times D times log 1 over epsilon. Okay? You can check if you don't believe, but log n epsilon f L2 mu n, and that's regardless of the empirical measure, is less or equal than C times D times log 1 over epsilon. Now, another point you should note is that although here I have to take the integral from 0 to infinity, but in fact I don't have to take the integral from 0 to infinity because, or at least you can look at it from here or from here, because my class is a class of functions all bounded by 1. So in L2, right, in L2 mu n, the diameter of the set is 1. Right? What's the worst L2 norm I can get? The worst L2 norm I can get is the supremum of f in f of 1 over n sum f at xi squared half. That's the L2 mu n norm, and that's the worst one over the class. Okay? So these are all bounded by 1. The sum is bounded by n. You divide by n, you get 1. You take the square root, it's still 1. It's bounded by 1. So the class is contained within the L2 mu n unit ball, meaning that if I allow a radius of a ball being larger than 1, I can take 0 as a cover. So I need just one function to cover the entire class, because the radius is big enough, which means that the log covering numbers for epsilon greater than 1 is 0. So in fact, I don't take the integral from 0 to infinity, I take the integral from 0 to 1. So you plug that in, and you get that Rn of f modulo Sn is bounded by some absolute constant, the integral between 0 and 1, square root of the log covering numbers. So you have square root d times square root of this, and square root of this, so log half 1 over epsilon. The epsilon, right, just to make sure I can have here 2 over epsilon so we won't have any problems. It shouldn't matter. Okay, and this thing converges. Near 0 decays, it doesn't increase quick enough, not a problem. So this is less or equal, and this is an absolute constant. It has nothing to do with the class, it's just this number, this integral, c square root of d. So for every sample I select, this kind of conditioned Rademacher averages is something of the order square root of d. So once I take the expectation, it's still bounded by square root of d. So Rn of f is bounded by c square root of d, where c is an absolute constant. Okay? Look at the sample complexity we have. Sample complexity tells you that the sample complexity for a VC class is of the order maximum between d over epsilon squared and log 1 over delta divided by epsilon squared. Okay? That way you can remove some of the logarithmic factors. But that's not a big improvement. That's not a big deal. For that, this wasn't worth the effort. The more interesting bit comes when I'm looking at classes with polynomial fat Chattering dimension. So again, my class of function is bounded by 1, and assume that fat epsilon f is bounded by gamma epsilon to the power p for some p between 0 and infinity. Okay, so you have an estimate on the growth rate of the fat Chattering dimension as you decrease the allowed margin, in a sense. Okay, we had a result that told us how to control the LP covering numbers in terms of this parameter. Remember, we had a result that says that the log covering numbers is bounded by an absolute constant times fat at a scale proportional to f times log squared 2 over epsilon. So you plug that in and you get something which is an absolute constant gamma epsilon to the power p log square root over epsilon. So that's an estimate on the L2 empirical covering numbers in terms of the fat Chattering dimension. Again, these are uniform bounds. Okay? They're true for any empirical measure. Now, you want to use that and plug it into Dudley's inequality over there. Where do you expect to have a problem? This integral diverges for p greater than 2, right? If you look at 1 over x to the power 1 over x to the power q, this integral diverges near 0 if q is greater than 1, and here I take the square root, so instead of p I'll have p over 2. So as long as p over 2 is smaller than 1, you're fine, which means as long as p is less than 2, you're fine. So Dudley's entropy bound will work in this case only for p smaller than 2. For p greater or equal than 2, you need some different approach. Luckily for us, one can generalize Dudley's entropy inequality and get some more complicated form, which will also be an upper bound for the Rademacher complexities, and in which case you can handle cases where the integral diverges. And you have these in the notes, and I'm not going to mention that. I'm not going to do the complete derivation here. But in general, what you can get is the following. So in the case I've mentioned here, Rn of f modulo Sn is bounded by an absolute constant times gamma to the power half the following. 1, if p is between 0 and 2, log squared n if p equals 2, and n to the power half minus 1 over p if p is greater than 2. Now, this result is, in my opinion, quite remarkable because it tells you that, well, let me mention one thing before I continue. Another thing you can show that if you have an equality here, if this is indeed the growth rate of the fat chattering dimension in terms of epsilon, then this bound is tight. This bound is tight up to the logarithmic power. Maybe you can improve 2 to 1. And of course, this is tight. So if you know that the fat chattering dimension behaves polynomially, which is the case in most of the interesting classes, then this is the best you can hope for. This is a tight bound. If you're looking for a bound which will hold for every sample, this is what you get. And this tells you that something changes when you go from p between 0 and 2 and p larger than 2. It's sort of a certain phase transition between classes which are very, very small and classes which are large. And it's something that the former analysis didn't show us. At the analysis using the classical approach, passing to an epsilon cover and treating every function separately, didn't show us. You would have sort of a continuous sample complexity as a function of p. We had 1 over epsilon to the power 2 plus p as the sample complexity, as the leading term. Here, even though I haven't written the sample complexity estimates yet, it's clear that something happens at p equals 2. And in fact, you can show that something does happen at p equals 2. Up until now, we've been talking about the uniform law of large numbers. But in a similar way to the uniform law of large numbers, you can talk about what's called the uniform central limit theorem. Okay? You have the central limit theorem, and you want to extend it to hold uniformly over a family of functions and not just over one. And it turns out that if p is between 0 and 2, you have the uniform central limit theorem. If p is greater than 2, you don't have the uniform central limit theorem. And for p equals 2, there are cases for which it will hold and there are cases for which it won't hold.
Can you be a bit more explicit?
I'd rather not. I don't want to formally define, well, let me just, the central limit theorem tells you that this random variable converges to its expectation. Okay? In any nice way you want, with probability or almost surely whatever. That's the law of large numbers. The central limit theorem tells you that if you normalize this by square root of n, this will converge in probability to a Gaussian random variable. Okay? So this would converge to a Gaussian. Now there's a way of formally, it's in the language of Gaussian processes, and I don't want to, of empirical processes, and I don't want to get into the formal definition, when you can ask, when does this thing converges to a Gaussian process indexed on a class of functions? If this happens in the appropriate sense, you say that your function class satisfies the uniform central limit theorem. And just like that, the law of large numbers is a weaker version in the hierarchy than the central limit theorem, the uniform law of large numbers is weaker than the uniform central limit theorem. So here, we sort of took all the possibilities of having the uniform law of large numbers at the polynomial scale. That covers all the spectrum if you go on the polynomial scale. And now you have sort of a finer separation. If p is here, you have a relatively small class because it satisfies the uniform central limit theorem. If p is here, then your class is too rich. You can't do much. It's sufficiently small to ensure a law of large numbers, but it isn't sufficiently small to ensure a central limit theorem. Okay? And those of you who are interested in sort of uniform central limit theorems, you can look at the books of Dudley. He has a book from 1999, and of course the classical book of Talleyrand and Ledoux. But I'm not going to get into that any further. But the good thing is that the point p equals 2 is not meaningless. If I could have explained why something strange happens at p equals 2, it would have been uncomfortable because you would assume that your boundary is loose somewhere, or that you have a problem. But something happens exactly at the point where you expect it to happen at p equals 2, under the assumption that you know something about Gaussian processes. Now, if you take this and plug that into this equation, you get the following. You get so you get that the sample complexity, I'm not going to write I will write, probably if fat epsilon f less or equal than gamma epsilon to the power minus p, then the probability of the supremum f in f greater than epsilon less than delta if provided that n is greater than or equal than some absolute constant. Well, let's write it a constant which depends on gamma and on p, and you can specify it. I just don't want to. Let's write it this way. The maximum between 1 over epsilon to the power p and log 1 over delta over epsilon squared. Okay? Now remember what we got using the old approach. The old approach gave us that the sample complexity is of the order 1 over epsilon to the power p plus 2. Okay? That was the old bound. If you had this estimate on the fat chattering dimension, the sample complexity was something of the order 1 over p plus 2. Here you get something which is, forgetting the log terms, something of the order 1 over epsilon to the power maximum between p and 2. So in some sense, if your class is very, very small, corresponds to p between 0 and 2, you get the absolute minimum you can shoot for, a sample complexity of 1 over epsilon squared. If your class is slightly larger, then you need to pay a penalty, which is this. Okay? So again, something changes at p equals 2. Not surprising because we've got a sample complexity based on this, sample complexity estimate. Now, another significant point from this analysis is the fact that this bound, this kind of argumentation, is a worst case bound. In what sense? How do I go from this bound to the definition of Rn? I take the supremum over all samples. But now, assume that the probability measure that I have is nice in the sense that it excludes bad samples. So now I'm sort of leaving the uniform result, having something uniform over the measure, and see how much advantage I can make by having a good measure. Okay? So this bound completely ignores the existence of a measure. I'm just replacing the average over this by the supremum. But in general, there may be some cases where the average would behave in a nice way. Okay, so that's one point I want you to remember. Another point is that this is an entropy-based bound. Maybe there'll be some cases in which it's worthwhile to compute the Rademacher averages directly, though it seems difficult. And one such case is the case of kernel machines, where you get good bounds on the Rademacher averages using a direct approach and not this. I haven't talked about this at all, and it's not even in the note, but the problem of estimating the entropy numbers or the covering numbers of kernel machines is very difficult. Okay? Bob Williamson, Alex, and Bernard had works on that. I had some works on that. It's a very non-trivial question. But since entropy numbers or covering numbers are only a way of bounding the Rademacher averages, maybe I can bound the Rademacher averages in a relatively easy way without having to resort to all this complicated machinery. And that's the main idea. Sometimes it works, sometimes it doesn't. Unfortunately, most times it doesn't. And for kernel classes, we're lucky enough that it works. So again, I'm not going to go into all the details, or any of them for that matter, actually. So example, kernels. So we had essentially 1.5 courses about kernels. You had Bernard's course and half of Alex's course. So I assume that by this time you know what are kernels, but I'm going to, just to make sure that you like my notation, I'm going to just say a few words about that. Okay? So you start with a function of two variables which you assume to be positive definite, and now I'm not sure if it was presented in this way, and you have a probability measure on your space. Now, using this function of two variables and the probability measure, you can define an integral operator. This operator maps functions into functions. So for every f, I define t of f at the point x as the integral over the space of kxy f of y d mu y. Okay? Now, this is just a mapping between two Hilbert spaces. But using this mapping, you can define what's called the reproducing kernel Hilbert space associated with this integral operator. And the way to do it is to use Merciless theorem. Now, Merciless theorem I lost the eraser. Ah, yes, thank you. That's the price you pay for being short. So Merciless theorem tells you that you can represent k of xy as sum I1 to infinity lambda I phi of x phi of y, where lambda I, where phi I are the is a complete orthonormal basis of L2, but more than that, they're the eigenfunctions of the operator t. So t of phi I will equal lambda I phi I. That's the definition. That's Merciless theorem. Using this, you can define the feature map and the reproducing kernel Hilbert space, and I'm not going to get into that at all. The one point I do want to mention, which is a very significant point and people ignore it all the time, is that this result isn't true. The way I've written it, it's true, but it isn't true for every x and y. It's true for every x and y as long as in some sense you measure seeds all the points in the world. So I'm making an assumption that you have a reasonable measure, that you don't just look at the part of the world and ignore another part of the world. If this is the case, you then can say that this holds for every x and y in your world. Using this, you can, again, as I said, define the reproducing kernel Hilbert space. You can define the feature map, and you can define the kernel class, I denoted it as fk, as, okay, all the functions of the following form. You compute the function at a point using the inner product of beta and phi at that point, where phi is the feature map. The inner product is now in the reproducing kernel Hilbert space under the constraint that the L2 norm of beta is less or equal to 1. Okay? So that's the definition of the kernel class. Equivalently, you can say that it's simply all the functions which are in the unit ball of the reproducing kernel Hilbert space. You can describe this class in terms of the image of the unit ball under a certain operator. There are about 3 different equivalent ways of defining it, and I'm not going to get into that at all. The point is that using this representation, it's not too difficult to compute the Rademacher averages. And I'm not going to do that. All I'm going to tell you is the following fact. Let's do it over here.
Can you say again what that says?
This one?
Yeah.
Okay. This one you understand? You want the equivalent things? This is, you look at the set of all functions defined as the following way. You define the reproducing kernel Hilbert space, right? That's what I call HK. So you have the inner product there, and you've defined the feature map using, maybe it should be like that. You define the feature map using this Mercer representation, okay? So now, once you have this inner product, you look at all the functions which are of the following form. The value of the function at the point x is given by the inner product of this representation vector times this vector. Right? This vector would be constant, so maybe I should say a few more words. This vector, in some sense, represents the point x. Okay? It's the way you map x. This vector is simply your representation of the function. Okay? So it's the vector representing the function, inner product with the vector representing the point. The equivalent way of defining the reproducing kernel Hilbert space, those of you who like this stuff, it's just as a Hilbert space in which all the point evaluation functionals are continuous. And that's exactly what you have. This is equivalent of the point evaluation functional. Right? You can equivalently say that the inner product of a function f in the reproducing kernel Hilbert space with the point evaluation function, the element representing the point evaluation function of the reproducing kernel Hilbert space is just f of x. And you can do it either way. You can do it like that and then recover this, or you can do it like that and then recover this. It's just a matter of taste. But the significant fact here is that for kernel classes, you can get a direct estimate on the Rademacher complexities, a direct bound. So, but you have to be a bit careful. Let K be a kernel. Let mu be a probability measure. Omega. And set lambda I to infinity to be spectrum of T. Okay? So these are just the eigenvalues of this integral operator. Okay? Now, then, the expectation over x, the expectation over epsilon, supremum of f in fk, sum epsilon I, f at xi, is equivalent, and I'll say in a minute what's that, to sum I equals 1 to infinity lambda I to the power half. Okay? There are these two delicate points here. The first delicate point, which is very, very important, is that this expectation, these random variables, are distributed according to this probability measure. So in some sense, the probability measure is represented by the definition of the integral operator and computing its spectrum, because the spectrum can change if you change the probability measure, right? Clearly this operator, the eigenvalues of this operator, might change if you take a different probability measure. Okay? So assume you fix the probability measure, you compute the eigenvalues of this integral operator, then the Rademacher complexities, first of all, are independent of n, right? So in some sense the class is small, but you can bound them from above and below by an absolute constant times this, which is just the square root of the trace of the operator. Okay? And using this result, you can get a generalization bound for unit balls in a reproducing kernel Hilbert space. Okay? Now this bound is tight, and it uses a result which is very difficult to show, in fact, which involves various tricks you need to compute this. And I'm not going to get into that at all. But if once you know, and I'll just tell you what the step is. The step is to show that this thing is essentially the same as this thing. Once you know this is relatively a straightforward computation. Going from this to this thing is difficult, and I'm not going to get into that at all. Okay? So
there's a square missing, but it's lambda I?
No, it's like that. It's the square root of the trace. Okay, square root of the trace. Now, these are essentially the most interesting example. I mean, you can compute the Rademacher averages for many, many classes once you know the fat chattering dimension or the VC dimension. Then there are sort of composition theorems telling you that if you have a class and you can decompose it in some sense to smaller and simpler classes, then you can use the smaller classes to construct the bigger one. There are various tricks of doing that, and again, I'm not going to get into that at all. All I wanted to convince you is that using the Rademacher averages, you get much better bounds when you combine them with Talleyrand's approach compared to the classical approach. Okay? The next thing I'm going to do, and that's be the topic of my last lecture, is to completely forget this stuff in a sense and focus on the problem I started with. Okay, the problem I started with was the following. Okay? What's the probability that there exists a function in your class for which the expectation, the empirical expectation is small, but the actual expectation is large? Okay? That's what I wanted to show. And the first step I did was a very naive step, because that's all I knew how to do, is to reduce this to a Livenko-Cantelli condition, to the uniform law of large numbers. And since I believe the Talleyrand's result is the best I can get, I can't hope to get an error sample complexity estimate which is better than 1 over epsilon squared. But again, in real life, real learning algorithm produce rates which are better than 1 over epsilon squared. So maybe I've lost a lot by going from this to the uniform law of large numbers, right? Especially since I know that my result in the uniform large numbers are tight. So the question is, how do I estimate something like this? And the idea which I'm going to talk about in my final lecture is to show you that you can do the following thing. You can bound this quantity by a uniform law of large numbers, and that's not big news, with one difference. It's not going to be the law of large numbers for this class. It's going to be a law of large numbers for a different class, which you can get from this one, with an interesting property. The variance, the worst variance of every one of the class members is about this order. So what we will get is something of the result. This is bounded by probability, the supremum, let's say, of h in h, mu n h minus mu h. So far, no big news. But here I'm going to have h of epsilon. And h of epsilon is going to have the property that for every h in h epsilon, the expectation, variance, of h squared is going to be bounded by, let's say, epsilon, maybe 2 epsilon here. So what you would get is the law of large numbers, true, but the deviation you're interested in is of the order of the largest variance of a class member. Now if you recall Talleyrand's inequality, which I wrote on the blackboard, sigma appeared there. Right? Sigma is the largest variance of a class member. And I'm going to be able to exploit this transition and the fact that this happens to get a considerably better sample complexity rate. And I'm going to be able to get, for example, for VC classes, to go from 1 over epsilon squared to 1 over epsilon. So I'm going to solve a different problem. I won't get 1 over epsilon for the law of large numbers for the VC class. I am going to get 1 over epsilon for something like this for VC classes, and the way I'm going to do it is going from here to the law of large numbers under an additional assumption that the largest variance is of the order of the deviation. Okay? And then I'm just going to use Talleyrand's inequality. The interesting thing is that because of that, right, the sample complexity for this would be essentially based on the same kind of argumentation. So now, instead of the Rademacher complexities for this class, we would use the Rademacher complexities for this class. So what we will have in some sense is the Rademacher complexities of a class constructed in a way from F, and it's a very simple way. I mean, it's not such a big thing to construct this class. But not the entire class, but the intersection of a class with a ball, because I know this. And that's what led Peter Bartlett, Olivier Bousquet, and me to introduce the idea of localized Rademacher averages. So the Rademacher averages, but not of your entire class, but of the intersection of your class with a ball, and I will show you that you can get improved bounds. For example, for kernel classes, instead of this, what you would get at the localized averages, so it would be something like 1 over square root of n, the same thing, supremum of f in, let's call it h epsilon of this, would be of the order, but instead of this term, what you will have is some I equals 1 to infinity, the minimum between lambda I and epsilon to the power half. And this will give you much better bounds for kernel classes in particular. Okay? So that's what I'm going to do in the next talk. I'm going to show you how to go from this to this, and I'm going to show you how to compute Rademacher averages using entropy in the localized version. And the final thing I'm going to do is to sort of give you a brief overview on a computable version of the Rademacher averages. So this, in some sense, is a global condition. Okay? You take the expectation over all possible samples. What I would like to do is to replace this with something which is data dependent. Right? You give me a finite sample, I can, instead of computing this, compute a similar thing on the fixed sample and say that in some sense this represents this. And I will be able to do that. So that's what I'm hoping to do on Friday. So thank you for your patience.